Welcome to a slow, beginner-friendly lesson on hashing with hashlib, made for absolute beginners. A new phase begins. Today you meet one of the most useful ideas in computing, a hash. A hash is a short fingerprint for any piece of data. Feed Python a word, a file, or a whole book, and it gives you back a fixed length string that uniquely identifies what you fed it. Python ships with a built-in tool for this, hashlib. We focus on the SHA-256 algorithm today. By the end you can fingerprint a string, compare two fingerprints, and explain why hashing is the backbone of security on the web. The fingerprint idea: a hash is a short, fixed-length string that acts as a fingerprint for some data. Feed in the word hello, get back a fixed hex string. Feed in hello again tomorrow, you get the exact same string back. That is the rule, the same input always produces the same hash. But change even one letter, capital H, lowercase lo, and the hash is completely different. Not similar, not close. Different. That is what makes hashing so useful. Same input, same mark. Here is your first hash. Import hashlib. Then call hashlib.sha256, passing in the bytes of the word hello. We pass bytes, not a string, so we prefix the string with a lowercase b. The result has a method called hexDigest, which returns the hash as a long string of hex characters, 0 through 9 and A through F. That 64-character string is the SHA-256 fingerprint of the word hello. Always. Anywhere. Anytime. Your first hash. Notice the lowercase b in front of the string. SHA-256 works on bytes, not on text strings. Computers store everything as bytes underneath, so we have to encode our text into bytes first. You can do it two ways: prefix the literal with b, or call .encode on an existing string. If you forget and pass a plain string, Python stops you with a clear type error. Encode first, then hash. Encode first. Watch how faithful hashing is. Hash hello twice and you get the exact same fingerprint both times. The same input always produces the same output. This is called determinism. But hash a capital H followed by lo, hello, and the hash is completely different. Not one character off. Entirely different. This sensitivity to input is what makes hashes so good at detecting even tiny changes in data. Faithful and sensitive. 4 properties make hashes special. First, deterministic, the same input always gives the same hash. Second, fixed length, SHA-256 always produces a 64-character hex string, whether you hash one word or 1 gigabyte. Third, one way, given a hash you cannot work backwards to the original data. Fourth, the avalanche effect, flip a single bit in the input and the entire hash changes. These 4 traits are why hashes power passwords, file checks, blockchains, and digital signatures. 4 key properties. Every piece of data can leave a unique fingerprint. A small mark that identifies the whole thing. A unique mark. You saw hexDigest, but there is also plain digest. The difference is the output format. Digest returns the raw bytes, a list of byte values that often include non-printable characters. HexDigest returns those same bytes as a hex string, 2 readable characters per byte. For almost everything you do, storing, comparing, printing, sharing, you want hexDigest. Reach for raw digest only when a library specifically asks for bytes. Hex or raw bytes. Sometimes you do not have all the data at once. You might read a stream in chunks. For that, create an empty hasher with hashlib.sha256 and call update as each chunk arrives. The hasher keeps building internally. When you are done, call hexDigest. Here we feed hello, then space, then world, and the result is exactly the same as hashing hello space world in one go. Update lets you hash data of any size, no matter how it arrives. Feed data in pieces. Comparing 2 hashes is just string equality. Compute one hash, compute another, then ask, are they equal? If yes, the underlying data is the same. If no, the data differs somewhere. This is the foundation of integrity checking. Someone sends you a file and its expected hash. You hash the file yourself, compare, and if the hashes match you know the file arrived intact. Simple string equality doing serious work. Equality does the work. A hash is itself just a string, so you can hash a hash. Compute the SHA-256 of hello, get back the hex string, then encode that hex string and hash it again. You get a different but perfectly valid hash. This is exactly how proof-of-work systems like Bitcoin chain blocks together. Each block includes the hash of the previous one. Hashing a hash is allowed, deterministic, and surprisingly useful. Chain them together. Hashing is faithful. The same input always makes the same mark. Change one letter and the mark is new. Identical inputs match. Hashlib offers many algorithms. Run algorithms available and you get a set of names: SHA-256, SHA-512, SHA-1, MD5, Blake2B, and more. They differ in output length and speed. SHA-256 is the modern default, long enough to be safe, fast enough for everyday use. SHA-512 gives a longer hash. MD5 is still in the library for backwards compatibility, but it is broken. Researchers can forge collisions. Never use MD5 for security. Stick with SHA-256 unless you have a specific reason. Many algorithms exist. A word on MD5. It is still in Python because the world has decades of old files hashed with MD5, and you may need to read them. But MD5 is broken for security purposes. Researchers can craft two different inputs that produce the same MD5 hash. This is called a collision. So MD5 is fine as a quick checksum to detect accidental corruption. It is not safe against an attacker who wants to forge data. For anything security related, use SHA-256 or a stronger family. MD5 is legacy only. Here is the fixed length property in action. Hash a 5-character word, you get 64 hex characters. Hash 1 letter, still 64. Hash a million letters, still 64. SHA-256 always returns 64 hex characters, no matter how much data you feed in. This is why hashes are so convenient to store and compare. The size is predictable. The length tells you nothing about the size of the original input. Always 64. Wrap the hashing in a small function so you can reuse it. Define SHA-256 text that takes a string, encodes it, hashes it, and returns the hex. Now you can hash anything with a clean call, SHA-256 text of hello. This is the habit to build. Once you understand the steps, hide them behind a clear function name so your real code reads like English. Wrap it cleanly. Why is 64 hex characters enough? Each hex character has 16 possible values, so 64 of them give 16 to the power of 64 possible hashes. That number is roughly 2 to the power of 256. It is astronomically larger than the number of atoms in the observable universe. Finding two inputs that hash to the same value by trying random inputs would take longer than the age of the universe on every computer on Earth. That is the security promise of SHA-256. Astronomically large space. Hashes are everywhere once you start looking. When you download a large file, the publisher often publishes a SHA-256 hash alongside it. You hash your download and compare. Passwords are stored as hashes, never as plain text. We have a whole lesson on that next. Every Git commit is identified by a SHA-1 hash of its contents. Digital signatures and TLS certificates rely on hashes. Blockchains chain blocks by hashing the previous block. One idea, infinite uses. Hashes are everywhere. A hash is a one-way street. From data you get the mark. From the mark you cannot recover the data. Cannot walk back. Quick recap. Import hashlib. Pass bytes to SHA-256. Call hexdigest to get the fingerprint as a hex string. The same input always produces the same hash. The output is always 64 hex characters. Use SHA-256 for anything security relevant. MD5 is broken, leave it for legacy checksums only. You now have the foundation. Next we hash entire files. Hold these 4 lines. In one breath, a hash is a fixed-length fingerprint for any data. The same input always produces the same hash. The tiniest change to the input produces a completely different hash. In Python, import hashlib, call SHA-256 on bytes, and read hexdigest. Use SHA-256 for anything that matters. The next lesson takes this idea to entire files. One breath, fingerprint. Next we hash entire files. You will learn to read a file as bytes, feed those bytes to a hasher, and produce a single fingerprint for gigabytes of data. We use chunked reading so even huge files fit in memory. And we build a real function that verifies a downloaded file against its published hash. Hashing goes from a string trick to a serious tool. Files come next. If you want a quick practice, hash 3 similar words and compare the first 16 characters of each hash. Python lowercase. Python with a capital P, Python all uppercase. Same root word, totally different fingerprints. When that surprise wears off, you have internalized the avalanche effect. Then try hashing a sentence and changing one space. Watch the whole fingerprint change. 3 words, 3 marks. Think of the journey from a string to a hash as a small pipeline. You start with text in your head. You encode it into bytes so the computer can work with it. You pass those bytes into hashlib.sha256, which crunches them through many rounds of mixing. You call hexdigest to read the result as a readable hex string. 4 steps, always in this order: text, encode, hash, hex. Hold this order and you will never get lost. The order is fixed. Thanks for learning the SHA-256 fingerprint. Next we hash entire files. See you on files next.